And the easiest things to understand what kind of the symmetry each molecular orbital has is given by the index chart, which is a summary of the symmetry molecules categorized in each group. And this index chart is a summary of the symmetry of not only the molecular structure, but also the molecular orbitals included in the molecule. So that's very useful. For example, here, this is an index chart for C2B molecules, which is a category of the SO2 we studied right now. And there are very important information in this chart. Okay. Now, first, this row, the first row, includes the symmetrical operations for C2V molecules. So you could know this more to understand the symmetry of this molecule or molecular orbital included in C2V. You have to check the operation of E, C2, and sigma V and sigma V dash. And by applying the symmetric operation, you need to obtain the index number for the transformation matrix, right? So, for example, what we obtain here is we obtain the 1, 1, minus 1, 1, minus 1, which is included in the B1, 1 minus 1, 1 minus 1. So the molecular orbital P2 is actually included in the B1 symmetry. And also, if you look at P2 orbital 1, 1, minus 1, minus 1, which is included in the 1, 1, minus 1, minus 1, it is categorized into the A2 symmetry of molecules. So again, let me remind you, this vertical column means the molecular orbitals, the symmetry of the molecular orbitals included in the C2V molecules. Okay. So actually, what we could obtain by calculation are included in the A2 or B1 type of symmetry of the molecular orbitals. And very useful information. And you can see from the chart that, again, let me summarize, it's a molecular orbital for the molecules in C2V symmetry are all categorized into A1 or A2 or B1 or B2 type of the symmetry. All right. And to understand if the molecular orbitals you are thinking about is so which category each molecular orbitals are can be checked by the orbital symmetry by applying these four symmetrical operations, EC2, sigma V, and sigma V dash dash, and check the transformation matrix and calculate the index value. Okay, and the molecular orbitals that included in the A1 symmetry is given by the small a1. Probably you've seen this kind of the expression in the spectroscopy or some optical transition literature and so on. And the one thing I would like to remind you that is that in the example of the C2V case, all the molecular, all the symmetric operation was reduced to the one-dimensional. So the transformation matrix was only the number in the case of like this. So only one number, single number. That's why this number is directly equal to index value. However, in some cases, it is reducible. And sometimes the transformation matrix is actually still a remainder matrix. In this case, the index becomes 2. And for the index can become the 3 for some of the molecules. Okay? And in a one-dimensional, the symmetry of the molecular orbitals is referred as A and B, right? That's why in the C2B molecular orbitals are given by A and B. However, if it's two-dimensional, it's written as E, and then three-dimensional, it's T. And you can find in a chart like this, in a C3B chart, you could see the index value is actually 2 in here, right? This is what you can learn from the index chart. Okay. Then move on to apply to know the molecular orbitals information from the example, right? So first, let's check out the symmetry of the px orbital of oxygen in H2O. So please think about it for a while by stopping the video and do it for yourself. Okay, then let's check out this. So H2O is categorized into the C2V orbital, C2V group, same as SO2. So H2O, right? The molecular orbitals in H2O must be either one of the A1 or A2 or B1 or B2, right? So now when we think about the oxygen orbital, and the p orbital of oxygen, right? Right, this one. So what you have to check is you have to check the four symmetrical operation like E, C2, and then sigma B, and then sigma B dash. And by applying the E operation, of course, the index is 1. For C2 operation, the molecular orbitals are the flip, so it's going to -1. And the sigma B and the sigma B dash, this one gives 1 -1. So that means that this is categorized into this. So it's going to B2 category, no, B1 category. So the molecular orbital is given by B1, small b1, right? However, there's easier way, much easier way to understand the molecular orbital symmetry by using the index chart, which is given by here. In the index chart, there's some X, Y, and Z, and X, Y, Z, Y, and Z, X, Y, Z, or something like that. This is an indication of p orbital and d orbital case. The molecular orbitals categorized into the C2b group, and then the p orbitals included in this molecules are already kind of categorized, right? So in the case of water, as I mentioned, the px orbitals in H2O has been already kind of here. Px is categorized into the B1 orbital, so you don't have to even check the symmetric operation for each of the molecular orbital. So very easy to understand that each of the molecular orbitals are categorized into the which orbital it is. And also in the case of d orbitals too. Right? So with that, we studied how to categorize the molecular orbitals into each of the molecular molecular orbitals included in the category of the groups.